Alright, so this workshop is going to be a lot shorter. There's basically two sections. The first section will be implementing a neural network model for tabular data, and then for the second section, we'll be using it for image data. So just for practice, we'll be using a data set from the internet. And basically, it's a data set of flowers, and then it contains different attributes. And then the goal here is to classify what type of flower that it is. So as you can see here, there is 150 entry points, and for each of those, there's 4 attributes. And but yeah. So the first step is importing the relevant libraries and then the actual data set. So as you can see in section 1, we import the NumPy library, the matplot library, and then the pandas library. And then in section 2 here, we insert the URL that contains the data set, and then we assign the names for each of the columns. So the first column is the length, the second column is width, and then the last column is class. And then in this last line right here, we we save the data set as a variable. So if we go on to Jupyter Notebook, we will see, whoops, wrong one. So this is the exact same thing on the slide. And then we just click run. And as you can see here, it shows a small subsection of the data set. So here you can see some of the values and just examples of some of the entries. So the next step is to do data pre-processing. And since this data set is pretty simple to begin with, the processing is relatively simple. First, we separate the attributes shown here, and then we load it into a variable called x, and then we isolate the class, and then we label that as the variable y. And then afterwards, we split our data set into a train and test set. So as you can see here, this is the training set of the attributes, the test set of the attributes, and then the train and test set of the class. Then here we specify that we want the test size to be 20% of the total data set. And then section 5 here, we scale the attributes. And then how we scale this is we basically normalize it to the mean of the attribute and the standard deviation. And this is just to help prevent bias when training the model. Because for example, some of the attributes have values that are 100 or 1000. It may be weighed differently than an attribute that's just like 1, 2, 3, or 5. So the idea of scaling it is that they all have the same weight. So here we set the standard scaler, which is just this formula here. And then we scale the data on the training set. And then we apply that scale on the test set right here. So here we just run the code that does that. And then next we need to train the model. So we import a function called MLP classifier. Note here it says k nearest neighbors, but we're actually using a different classifier. And then, so let's see. So here you see it says import MLP classifier. And then here we set the solving method, the alpha value, and then also this is the number of nodes in each layer. So as you can see here, there are 3 hidden layers. And then for the first layer, there's 3 nodes. For the second layer, there's 2. And then for the third layer, there's 3 nodes again. And then next so in order to train the model, we use a function called fit. And it basically uses the classifier that was created here. and then we fit it on the training data shown here. So this is the attribute and this is the class. And then we use that classifier and we predict the test set attributes. And the predicted classes are called y underscore prediction, as shown here. So next we test the model and see what the, I guess like the performance of the model is. So here we print the confusion matrix. And basically how the confusion matrix works is for everything in the diagonal, those are correct classifications because that means it's class 1, it was predicted to be class 1, it's class 2, predicted to be class 2. So for example, this one here, that's a misclassification because the true value, the true class is the second class, but then it predicts it as the third class, so then it gets it wrong. So we go here and we run the script. And as you can see here, the performance is pretty good. All of the test set entries are classified correctly except for this one. So that's a pretty high accuracy. Notice that these numbers are actually different from the numbers shown here. That's because the train and test set is split randomly each time. So you don't get the same results every time. But then also when you train the model itself, it has some randomness introduced into it. And that's why while the results are similar, it's not always the same. But yeah, basically, as you can see here, running a simple multi-layer perceptron model on a really small data set is really simple. Like it only took us 7 minutes to go through all this. But one thing to keep in mind is, so first let's look at the big picture of this exercise. There's basically 6 major steps. First, we load our data set. Then we isolate the features and then the class stored as X and Y. We split the training and test set. And then we train the model on the training set and test the model on the testing set. And then we view the performance. So it seems pretty simple. And in this exercise, it is simple. But it's important to keep in mind that for our actual project, it's very different. Like for one, the model we used here is pretty easy to understand. We used a 5-layer neural network model because there's the input layer, output layer, and then the 3 hidden layers, right? So that's 5 layers. But in reality, the model that we're going to use is probably going to be like anywhere from 10 to 30 layers. So then it gets much more complex and then it becomes very, I guess, not intuitive. And this is one unfortunate aspect of using neural networks. Because as you can see in this quote here, this professor is from NYU's Department of Computer Science, so clearly he knows what he's doing. But even he says that there's not really a good understanding of why these models work so well and how they can be improved. So that just kind of, I guess, like illustrates how complex these models are. And then also keep in mind this data set that we used. It only has 4 different features, as you can see here. Here's the first feature, the second, third, and fourth feature. But the model that we'll be using, we will have like hundreds, possibly even thousands of different features. So that makes the model much more complicated. And then because this model, the model that we just built is really small, that means there's also less parameters that need to be trained by the model and less hyperparameters for us to look at. But for a larger model, there's more of those that we need to examine, so then it takes longer to compute. And then also, lastly, that data set only had 150 data entries. Our data set has 86,000 pictures of individual cells. So these are all different factors on why our actual project won't be this simple. Alright, so let's get started on part 2. So this is where we use convolutional neural networks, which is, I guess, like a specialized form of neural networks, and it's used most commonly for image recognition, although it could be used for other things, of course. So for the sake of running the model quickly, we'll actually only be using 5% of the data set in this practice tutorial. So we will use a package called Keras, and it's basically a front-end API for neural networks, and then the back-end API is TensorFlow. And there's different layers that we can customize with Keras. And as an overview, look at the left section over here. These will be the different layers that we have in our preliminary convolutional neural network. So of course the first layer must be the input layer, and the last layer is the output layer. So before diving into all the layers in between, let's I guess go over what all of these different types of layers are. So for the input layer, you use this function shown here, and then we need to set the values for shape. And as you can see here, it says 125, 125, and 3. That means the input data is a 125 by 125 pixel image. And then the times 3 means it's an RGB because there's 3 different values for each pixel. And then for the convolution layer, we use the function called conv2d. And the 32 means there's 32 filters. And then each of the kernels and the filters is a 3 by 3 pixel size. And the activation function, as you can see here, is a ReLU activation function, also known as a ramp function. And then here we set padding equal to same. And basically what that means is we add padding to the input image so that the output dimension is the same as the input dimension. Then the max pooling layer is where we downsample the image, and then we set the pooling size as 2 by 2. So that means for every 2 by 2 subsection of our original image, it's downsampled into a single pixel. So the max pooling layer with a 2 by 2 area basically halves the dimension of our image. And then the flatten layer is basically where we begin developing our multi-layer perceptron after all of these convolutional layers. And it basically flattens each of the individual outputs from the convolution layer into a single layer in the multi-layer perceptron. Actually, just to illustrate this better, let me pull up a useful figure from the previous workshop, because it's kind of hard to visualize. No. So if you look at this diagram here, each of these small boxes you see here and there, those are the different values from all these convolutional layers. So what the flatten layer does is it puts all of these into different nodes. So this is one node, this is a different node, or neuron, however you want to call it. And then that's when we begin having a multi-layer perceptron shown here, rather than just the convolutional layers. Then the dropout layer, what it does is it removes some of the inputs. And so for example, when we set the rate to 0.3, that removes 30% of the inputs. So that seems pretty counterintuitive because you're basically, in some ways you could argue that you're losing information. But the reason why this is useful is because by removing some of the inputs, hopefully at least the idea is you can prevent overfitting, because you might be removing some inputs that are caused by noise rather than, I guess, like any actual useful features. And then lastly, we have the dense layer. And what the dense layer is, it's basically a traditional hidden neuron. It's a traditional hidden layer. And then we set the activation function as relu. The 512 means there's 512 nodes. So to visualize that, for example, this is a dense layer right here. So if we have a dense layer with 512 nodes, there will basically be 512 of these different boxes. So let's go back to look at the layer by layer overview. So we have our input layer, we have one round of convolution, we downsample it through max pooling. We repeat the same thing 2 more times, the second time here, the third time here. And now that we're done with the convolutions from layers 2 through 7, we flatten it in the 8th layer so that we flatten it into a hidden layer shown here. And then we have a dropout layer where we remove some of the inputs. Then we have another hidden layer and then another dropout layer that removes even more inputs. And then we finally have our output layer, which gives us the classification of the image. So if you run that on Jupyter Notebook through the script I gave you guys, you will get an output that is shown here on the right. And here it basically shows you the number of parameters that are in each layer. So as you can see here, the model has to train 15 million parameters. So that's why it takes a really long time. So in fact, since it takes so long, let's go ahead and get started on running the model while I'm explaining the rest. So here we import the packages and libraries. As you can see, it's loading because of the asterisk. And then we initialize our variables. So we want the image height to be 125 by 1, and then the image width also 125 pixels. This is the folder directory for training set and test set. This is the number of training samples and number of test samples. And then epochs is basically how many times we want to go through the entire training set to update the accuracy of our model. So here we customize all of the different layers. Like here's the input layer, convolution layer, max pooling, another convolution, etc. And then drop layer, and then the output. And this is all using the functions and schematics shown here. And if any of this is confusing, you can find more documentation at this link right here. So when we run this, we get this output that was shown in the PowerPoint. So I'm going to go ahead and train the model just because it takes a while, but alright, so it's getting started. Now let's go back to the workshop. So after we train the model, you should get an output that looks like this. Although it'll probably take a pretty long time to run, but as long as you can see the first few epochs, you know that it will work, and it's just a matter of time before it finishes the rest. So notice that on my computer, it takes about 90 seconds to run each epoch. I've been getting feedback from some other people. Theirs takes anywhere from 10 minutes to 1 hour, which is slightly problematic because here we want to do 20 iterations, right? So if it takes an hour for one iteration, then it'll take 20 hours to train the model. But yeah, as you can see on my computer, it takes about 1.5 minutes. So it takes 30 minutes for me to train this model. And here where it says validation accuracy, this is the accuracy of the test set. And then ACC here is the accuracy of the training set. It's really important to know the distinction between these two because the model does not use the test set at all to train the model. It only uses the training set. So as you can see through each iteration, the accuracy of the training set increases. And that's because each iteration, the model is updating its structure so that it gets a higher accuracy on the training set. And then theoretically, if the model is not overfitting, then you should see a corresponding increase in the test accuracy. And as you can see here, it fluctuates a bit at the beginning. Here it's 50% accurate, here it's 74. It drops back down to 51, and then 79, 72. But then eventually when you get near the end, as shown in these last two iterations, the accuracy somewhat stabilizes and it's much higher. So we can see here that our accuracy is around 85 to 90%. And this is, it's worth noting that these fluctuations tend to decrease as our data set gets bigger. Because here, for the sake of illustration and having everything be done quickly, we only use 5% of our images. Alright, so let's go back to, so as you can see here, while I was explaining that, it's finished one iteration, and then here it finished the second one, and it's currently working on a third one, and this is like the number of images that's currently working through. This is the estimated time that it'll take for the iteration to complete. So I'm going to pause this just because my laptop fan is kind of loud. But yeah, so the idea is if you let it run long enough, it eventually converges on a final accuracy that you can use as a, I guess, like a measurement of your model's performance. But yeah, that is everything.